Good day, everyone. So for today, we're going to learn first order differential equations which are not separable, nor homogeneous, nor exact. So if they're not exact, we say that they are inexact. So our goal for today is to make an inexact DE exact. So before we know that a DE is inexact or exact, we need to test by performing partial differentiation to the M expression and the N expression. So there are two methods of determining what we so-call the integrating factor that we will multiply to our inexact DE to make it exact. So method 1 has two cases under it, and method 2 is just a case of finding the integrating factor by inspection. So what is case 1 for determining the integrating factor analytically by means of a formula? So since you already took the partial derivatives of m and n, you're going to make use of those particular partial derivatives in this formula. So you are to get the partial derivative of m with respect to y and that of n with respect to x, and then you need to divide the difference between the two by n, and that should give you a function of x expression. Now it is a requirement that before you can use the formula for finding the integrating factor under case 1, that the corresponding function of x that you will be producing is solely a function of x. What does that mean? That your function of x should only contain the x variable. It should not have a y. If in a case will arise that your corresponding expression from this particular formula is a mix of x and y, you cannot use case 1. Then you have to go to case 2. If case 2 will not work, then you will have to resort to the second method, and that is finding our integrating factor by inspection. So in this particular example, we will use method 1, case 1, wherein we will try to see whether the corresponding function of x that we will be getting from this particular formula will be solely a function of x. So here in our example, your m is x squared plus y squared plus 1, and your n is x squared minus 2xy. What we need to do is partially differentiate the two with respect to y and x respectively. Now this is for the testing part whether our DE is exact or not exact. Now in this case, you see that the two partial derivatives are not the same. So we say the DE is not exact, or shall we say it is inexact. So what we're going to utilize now is case 1. So we will find the function of x using this formula. So we will copy the 2y for partial of m with respect to y, and we will copy 2x minus 2y for the partial derivative of n with respect to x. The corresponding expression from that would be negative 2 times the quantity x minus 2y. We factored out 2, which is common after we have added all the terms here. Now, this particular answer that we have will be divided by the n, which is x times the quantity x minus 2y. So it's readily cancelable, these two expressions, leaving us with negative 2 over x. So we would be happy because the corresponding function that we produced here is just a function of x. Then we proceed with applying this formula that the integrating factor phi is equal to e raised to the integral of negative 2 over x dx. Then the rest would be your calculus. So if you integrate this would be negative 2 ln of x. If you will simplify, that would be e raised to the ln of x raised to negative 2, and that would be x raised to negative 2, and that would be 1 over x squared. So we know that this is the integrating factor. And we will try to see whether after we have multiplied the original DE by this integrating factor, it would really be made exact. So we will do just that. and we multiplied. This is our original DE. So we multiplied this expression by x raised to negative 2, or that's 1 over x squared. So we do just that, and this will be the resulting expression. So you have a 1 for this, you have an x squared for this, and you have a y squared x raised to negative 2 for the middle term. In here, you will have a 1 minus 2x raised to negative 1 y dy. Now, let's check whether the new m and n are all now having the same or equal partial derivatives. So we differentiate the m sub 1 this time by y with respect to y. So that should give us 2yx raised to negative 2. 1 and x raised to negative 2 being a constant are all 0 in terms of their partial derivatives. Here we differentiate with respect to x, so that would be negative 1 times negative 2, so that would be positive 2x raised to negative 2y. So as you could see, using the integrating factor, we made the not exact DE or the inexact DE exact. If it's already exact, we can follow the procedure that we're using in finding the solution for an exact DE, but this time using the new m and n. So in this case, we integrate the m1 with respect to x. So we copy here our m1 and integrate it with respect to x. So the resulting expression is x minus x raised to negative 1 by power rule. Here, copy y squared, and this one is negative x raised to negative 1 plus gy. So we have a g of y here, and using the second method, we need to differentiate this expression with respect to y, meaning x will be kept constant. So this would be a 0, and this would yield a 2 and negative. So this would be x raised to negative 1, and this would be negative 2 x raised to negative 1 y plus g prime of y, and we equate it with 1 minus 2 x raised to negative 1 y. So this should be copied here, the n. We equated the n to the partial derivative of the f we got from the first integration, with the goal of finding the gy or the g of y. This is, by the way, negative. So both being negative, we can cancel them, and we can have the g prime of y being equal to 1, giving you a g of y equal to y. Now this is your your g of y already, which you will substitute to the first expression for f. And that would give you now the solution to the given DE. So x minus y squared over x minus 1 over x plus y equal to c. If we will multiply the entire expression by x, so it would be an x squared minus y squared plus xy for this, and that would be minus 1 equal to cx. Although from here, you already have the answer to our inexact DE. Now, what about case 2? Case 2 is just the same as case 1, still under method 1, only that this time we interchange the manner of subtracting the m and the n in the first case. So this time, it would be partial derivative of n with respect to x minus partial derivative of m with respect to y, and this time we divide by m. This would be our g of y. And just like the f of x in case 1, this g of y is expected to be solely a function of the y variable. Your integrating factor then would be equal to e raised to the integral of negative g of y dy. So exactly the same, only there's a pattern here, only that we divide by m, and this one is negative. Okay, we interchange the manner of subtracting these two. So if we will apply it here in this particular example, your m is y squared, your n is 3xy plus y squared minus 1. We integrate this one with respect to y. So that should give you a 2y, And this one with respect to x, that should give you 3y. Again, the two not being equal, the d is said to be inexact or not exact. So this time we'll try to see whether the g of y that we are expecting out of this formula is really only an expression of y. So we do just that. We copy the m, we copy the n, and then we divide by m. That's our, this is rather our m. So we divide by that. So this minus this over this. And this is our expression. Okay? We interchange the manner of subtracting here because it's negative. Negative here. It's supposed to be this one minus this. But since it's negative, so it's just like this minus this over this time by m. So this is our integrating factor after we use the formula. So it's a y. Then if you will test for exactness again, that would be left for you as an exercise. You'll be getting the partial derivative of the new m and the new n with respect to y and x respectively would be equal. So in this case, I did not anymore go through the testing again because it's really expected that once you multiply your inexact DE by its integrating factor, it will be made exact. Now, here is your new m, and this is your new n after we multiplied the original DE by y. Then we have the integration of the partial derivative of m with respect to x, which is the m with respect to x. So that should be y cubed x plus g of y. Then you are to differentiate this with respect to y. So that should be 3y squared x plus g prime of y. And you will equate this expression to the n with the goal of finding the g of y. So we cancel this 2. That leaves us with y cubed minus y. And then we use power rule. This is our answer. So this is the expression for the g of y here. So we copy the f that we have on top after the first integration, and then we copy as well the g of y that we got here on the previous step and substituted on the formula of the f to get the solution of our DE. So this is now the solution of our DE after we have multiplied this line by 4. You may wonder why. Why is it that there's no 4 appearing on the C? It's a given that an arbitrary constant multiplied to something that is fixed will still be yielding or producing another arbitrary constant. So nonetheless, it's still represented as C. So this is our solution for our inexact DE using method 1, case 2, wherein you use the formula that we have been provided for finding the integrating factor. So again, for method 1 and 2, you need to have f of x expression and g of y expressions that are solely a function of one variable. In the case of f of x, that should be x. In the case of g of y, that should be y. Now, method 2 requires a lot of good skill in manipulating, a good eye but that will be able to detect or should be able to see patterns in the combination of terms in your original DE. And it really requires a good foundation in differential calculus upon seeing the corresponding product of regrouping of your terms in the original DE. So this is still finding the integrating factor, but this time by inspection. So there is no formula to use, only using the concept of what we call as the exact differentials. Now, we'll be only using these exact differentials that you see here. So when we speak of the d of xy, it's just like you're going to have this expanded and determine its derivative. So this is just a product of x and y. So x dy plus y dx. Whereas when you see a d of x over y, that is a quotient of two variable expressions. So you have a y dx minus x dy over y squared. You use the same formula in the case of d of y over x, as you can see here. As for the arctan of y over x, we know that arctan from differential calculus is du over 1 plus u squared. So in the case of this one here, the y over x, your numerator answer here will be this entire expression. Y dx, or rather x dy minus y dx over x squared. It's because you're after the derivative of your y over x, and that should be written in the numerator. However, your denominator is 1 plus u squared, where your u is y over x. So if you're going to square the u, that would be then 1 plus y squared over x squared. If you will expand, that would give you an x squared plus y squared over x squared, which will cancel with the x squared that you have in the numerator, leaving you with this expression. So it's important that you memorize this common for exact differentials. And more or less a majority of your inexact DE made exact by using the method of the integrating factor might be using any of these four. Now, so we'll have this first example. So you have this. If you're going to test, it's actually right away in exact. Even by eye, if you're going to perform partial differentiation here, it's no way that they will be equal. I'm referring to the partial derivatives. So what we'll do, we'll have this mentally expanded. That should give you x dy and x cubed y squared dy. So that would be this expression you see on the second line. And you notice that y dx plus x dy was grouped together because in here, we will try to see if this will work. The x dy plus y dx. So we have that, and we replace this y dx plus x dy now by the d of xy, as you can see here. Okay, and then we leave the second term to x cubed y squared. If you notice, class, we have to deal with this expression because you cannot solely divide by x cubed only, because it will, the differential here rather is the d of xy, and it will render the first term non-integrable, though we have solved the product of the second term being now integrable. So we have to think of what we're going to do with this third line in our solution. That way, my two terms here can be readily integrable after I multiply the whole expression by that thing that would produce exact differentials, or that will make my terms readily integrable. So if I will divide this line by the quantity x cubed y cubed, then this one will have quantity x y raised to 3. And this one, if you divide by x cubed y cubed, will have dy over y. So if you notice, by dividing by xy raised quantity cube, this original expression, now we have terms that are readily integrable. So the u here is your xy, the n is negative 3. So if you use power rule, your answer will be xy raised to negative 2 over negative 2. In expanded form, it would be this. This is an ln of y, and since we have an ln, we can write an ln of c, or a negative ln of c, which does not actually matter at all. If you will transfer the ln of y here, both would be negative, so you can factor out the negative 1 and you will have the ln of cy. Then the negative and the negative here will just cancel each other, and if you cross multiply 2x squared on the other side, that should be now 2x squared y squared ln of cy that you have here equal to 1. This one actually came from the left side. So what was done is combine these two into two negative ln's, factor out negative 1, cancel it with the negative 1 here, and then after combining these two, you cross multiply the 2x squared y squared. that should leave you a 1 on this side and this expression on the right side. So that's how you manipulate your DE in such a way that you will produce a group of terms that will have exact differentials. And however, the remaining expression still has to be made integrable. So that really entails skill and experience in having to look at the terms in such a way that whatever you do to the entire equation, the main goal is for you to make all the terms in your DE integrable. So let's have another example still on inspection. And you have this 3x squared y dx plus the quantity y to the fourth minus x cubed dy equal to 0. You get to see a 3x squared here, and you get to see an x cube here. There must, if you look very closely and you try to look for a relationship, or you must rather establish relationships among the expressions here, you may notice that the 3x squared is the derivative of x cubed. So let's try to work our way here first. So you have 3x squared y dx copied, and this one also copied. This one and the dy is no problem at all because it's in terms of y and it's readily integrable. So what we're going to do here is, in the first term, if you notice, I'll try to get the y. The 3x squared dx, as I have mentioned, is actually the derivative of x cubed. So we write it as the differential of x cubed, which will yield 3x squared dx times y. So this replaces this. So actually, we just made use of the concept of differential calculus. And you have minus x cubed dy still and in here. Now, if you recall, we have this exact differential a while ago. And if you're going to make use of this exact differential, in these two terms here, your denominator should be a y squared. So what we do, you mentally divide the third line here by y squared. So if you divide by y squared, this one together with this would yield this one. Why? Because it would be y derivative of x cubed minus x cubed derivative of y all over y squared. So this d of x cubed over y is actually this divided by y squared. If you did division by y squared here, you should also divide this by y squared. So, amo ni nabilin. So, you have y squared dy. Then, when you integrate, in the case of the exact differential, you right away just simply drop the d. Because we know for one that dx integrated is x. So, it's the same principle you apply here. Integral of dx cubed y would be x cubed y. And this one will be using power rule. And again, here, there was some manipulation. That way, our c would be an arbitrary constant that could be readily combined with the y cubed over 3. If we integrate the entire equation here by 3y, that would yield a 3x cubed here. That would be y to the fourth here, and this would be cy. Although, this line is already sufficient for the form of the solution of this differential equation. This is just another way of presenting this line. Just in case later on, when you try to look for your answer on the choices, you know that there would be required simplifying procedures. That way, your answer as it is would look similar to one of the choices provided. So this is our final answer actually, which is equivalent to this other simplified expression. Now, if you're going to have the last example here on inspection, by the way, when you use method of inspection in determining the integrating factor, be ready for a lot of trial and error. It requires a lot of skill and experience, and if you're not comfortable with it, then stick to method 1. If method 1 will not work, then try to find other methods that were already discussed regarding handling first order differential equations. So let's see. In here, you have y times the quantity x cubed y on the first term, and we have this x times x cubed plus y dy. What's done here, if you notice, is we group. There is a regrouping of terms. That way, we will be able to see this exact differential again. So you have the y x cubed dx, so this one, and it's grouped with another y dy here, which is, if you factor out the x cubed, that would be x dy. So the first term here and the first term here were grouped together so that you get to see a y dx minus x dy. So again, notice the first term here, which has an x cubed, it's a differential of x, and then you have the y, and the first term here also, which is having an x cubed, but this time the x times the differential of y were grouped together here. The other one is y dx, factoring y out, negative y, and then you have x dy, but since it's negative here and that's negative, so this should be, and wait, if this is negative here, negative, and this one is also negative, then this should be a plus. So minus y times the quantity x dy. These were grouped also because this is the differential of xy. But this one is the differential of x over y. So recalling that x over y is this, if you look very closely, you need y squared here to make it an exact differential. So we divide by y squared line 2 with the goal that we will have an exact differential in the case of this term. So if we do that, you have now x cubed the d of xy, because this over y squared is this exact differential of x over y. This one is the differential of xy, and you have y. When you divide by y squared, that would simply be y. You got rid of this y, but you still have one y left in the denominator. Now, as you can see, this is not yet integrable because this one is not paired with any of this, and the same thing with this. So what we're going to do is divide the entire expression by x squared y, or rather, it's divide by x squared y, not 1 over x squared y. Why is that? If you divide x cubed by x squared y, that would be x over y. And x over y raised to 1 would be integrable with the differential of x over y. Now, if you will divide this by x squared y, this one, that would also be yielding an x squared y squared. Your u in this case will be xy, and your n will be 2. So now you can see that this is actually, this expression is xy quantity 2. So rules of exponent will help you integrate this one. The same thing with this. So if you will integrate this using the rules of exponent, your u is x over y, your n is 1. So you add 1, so, and then divide it by 2. It's u raised to n plus 1 over n plus 1. So the integral of this is this one. The integral of this using rules of exponent, because this is xy raised to the quantity negative 2, will be xy raised to negative 1 over negative 1. So since it's negative 1, it's in the denominator, and the negative here was made positive. And again, notice that there was some manipulation in the c. It's because we have a 2 here. It could be a c only, and this line is already your answer. The reason why we place a 2 under c is because we have a 2 on the first term also. So if we will multiply the entire expression by 2 xy squared, 2xy squared, because you don't have the y anymore. That will give you x cubed here, and 2xy squared would give you a 2 over y in here, and you have, wait, if you multiply by 2 here, so that should be a 2 x squared y squared. Wait, if this is an x cube here, this was multiplied by an x. The y squared was gone, so it was multiplied by xy squared. If this is multiplied by xy squared and 2, that should be 2y here. This one will not have a 2, and this would be xy squared. C, the 2 is gone also. So again, this line would have been sufficient, but if you want to simplify, this one was multiplied by 2xy squared to give you the final line, which is x cubed plus 2y equal to 6cxy squared. So this is how we make inexact DE exact by the use of the integrating factor using the two formulas. If the two formulas will not work, we can use the method of inspection that requires a lot of manipulation on the part of the user. That way, your regrouping will yield the exact differentials that were presented here and render the rest of the terms in your DE integrable. So that's it, class. We can make an inexact DE exact.